In the previous video, we learned about polyprotic acids. We learned that this means that we have multiple protons that are able to be ionized when they react with water. So here in this example, we have a generic diprotic acid, which reacts with water to form a monoprotic acid and an equivalent of hydronium. And this is governed by Ka1 and pKa1. And then this monoprotic acid can further react with water to form another equivalent of hydronium and the conjugate base X2-. And this equilibrium we said was governed by Ka2 or pKa2. And in the last video we learned about titration curves and how we can predict the position at the first half equivalence point, the pH at the equivalence point, and the pH at the second half equivalence point, right? And we talked about how this was the first pKa, this was the second pKa, so this is pKa2, this is pKa1, and then this intermediate position is the average of these two pKa's. So the titration curve would look like something like this. We shift through our first buffer region, we hit the equivalence point, we shift through the second buffer region, and then we have a second equivalence point, okay, before it levels off. So what I want to focus on in this video is thinking about the buffering aspects of polyprotic acids. So since we have two buffer ranges, that means this acid can serve as a buffer over two pH ranges, right? So we can serve as a buffer from one pH unit below our first pKa to one pH unit above, and then also we can center around our second pKa. So in the previous example, we saw that carbonic acid, which is H2CO3, has two pKa's. The first one is 6.35, so pKa1 is 6.35, and pKa2 is 10.33. Okay, so that means that carbonic acid can buffer pH range from 5.35 to 7.35, also from 9.33 up to 11.33. Right? So there's two buffer ranges here for carbonic acid. So when we're thinking about what's important, what you want to really think about is what pH you want to deal with. So if we wanted to buffer a solution at a pH of 7.0, so let's say your blood, then we would definitely not be dealing with this second pKa, but instead we would be working in this first buffering range, which we know deals with the conversion of, this first ionization reaction. So in the case of carbonic acid, the equilibrium we're thinking about is H2CO3 plus H2O becoming hydrogen carbonate or bicarbonate plus hydronium. So this is the equilibrium we're thinking about at pH 7.0. And what that means is that it's carbonic acid and bicarbonate that are the two species present at pH 7.0. Okay, if we happen to want to buffer at a pH of 10, well in that case it would be the second equilibrium that would play an important role. But at pH 7.0, that second equilibrium does not play a role in the speciation between different forms of our acid. So with that in mind, let's go ahead and think about how the abundance of carbonic acid, bicarbonate, and carbonate change as we progress through pH. So we'll approach this from this speciation curve perspective that we introduced a couple of videos ago. Okay, we know at the top here we have 100% species, in the middle we have 50%, and at the very bottom we have 0%. Okay, so moving along our axis here, we reach our first half equivalence point, our first equivalence point, our second half equivalence point, or the 3/2 point, and finally our second equivalence point. And as we're progressing along here, we're actually increasing in pH. So at the very beginning, we know we're starting with 100% carbonic acid. And we know that as we become more basic, so as we add hydroxide to this, we transition through the first half equivalence point, which is where 50% of this carbonic acid has been converted to bicarbonate, and by the first equivalence point, we're down to a concentration of 0%. So we have this type of curve where we are decreasing through the 50% mark at the half equivalence point, and we end up with a 0% at the first equivalence point. Okay, let's think about the basic form of carbonic acid, bicarbonate. It starts at 0. It's at 50% abundance at the first half equivalence point, and we've completely converted carbonic acid to bicarbonate by the first equivalence point. So we have a mirror image of what was going on with carbonic acid. So at the first equivalence point, we have 100% carbonate, which is now going to serve as the acid. Okay, so as it transitions through this second portion, as we become more basic, we're down to 50% at the second half equivalence point and down to 0% at the second equivalence point. So we end up with a curve that looks an awful lot like what we saw with carbonic acid, but we're now in the second equivalence region. Okay, we'll finish this up with thinking about carbonate. So with carbonate, we're starting at the very beginning with 0%. We're still at 0 all the way through the first equivalence. Okay, but once we reach the second half equivalence point, 50% of the bicarbonate has been converted to carbonate, and by the second equivalence point, 100% of our solution is composed of carbonate. So this curve then mirrors what we saw with bicarbonate. Okay, so as the pH is becoming more basic, we are transitioning from carbonic acid to bicarbonate and then to carbonate. Within the first buffer range, which is here, we have a mixture of carbonic acid and bicarbonate. Within the second buffer range, we have a mixture of bicarbonate and carbonate.